Hi everyone, I'm Wayne.
And I'm Ryan. For the last few months, we have been researching the chemical nature of interactions between copper-2 and C-peptides.
The importance of our research is that C-peptide has been shown to play a beneficial role in ameliorating vasculopathies and kidney dysfunction, but the lack of knowledge surrounding its cofactor is hindering advances in its therapeutic applications.
Endogenous peptides play many diverse roles in biology and are crucial to healthy physiology. Many reports have indicated that metal ions can have beneficial or detrimental effects on these peptides. Prior work has shown that C-peptide may depend on bioavailable metals and that C-peptide demonstrates beneficial behavior in the presence of divalent metal ions, such as copper-2. Copper-2 is shown to bind to C-peptide despite lacking common copper binding residues. We sought to determine this binding site despite obstacles such as simple primary structure and random coil tertiary structure.
We turned to mass spectrometry in order to verify copper-2 binding to C-peptide. The molar mass of apo-C-peptide is 3020.29 grams per mole, and its spectrum shows molecular ion peaks at 1510 and 1007, corresponding to the doubly and triply charged molecular ions. We added one equivalent of copper-2 to C-peptide, and the generated spectrum contains peaks at mass over charge values of 1540 and 1027. These values indicate that copper is binding and at a 1-to-1 stoichiometric ratio of metal to peptide.
To understand exactly where copper is binding to C-peptide, we turned to NMR spectroscopy. We identified what proton resonances correspond to which protons of apo-C-peptide. We then took a NMR scan of copper-2 with C-peptide. When copper is bound to C-peptide, the proton resonances at 8.6 and 2.7 parts per million, representing glutamic acid 3 and aspartic acid 4, are obliterated. We believe this destruction of signals to be caused by paramagnetic broadening due to copper being present at these amino acid residues. The backbone protons have small or negligible shifts, which indicate that there is little structural rearrangement. As these residues are not usually present in copper binding, the coordination complex was probed using EPR spectroscopy. The data acquired suggests that copper was bound in a square planar geometry. Further analysis was done consulting with the PSATch and Bloomberg truth tables, which suggests that the environment binding to copper is made up of either 4 oxygens with a total -2 charge, 1 nitrogen and 3 oxygens with an almost neutral charge, or 2 oxygens and 2 nitrogens with an almost neutral charge again.
Fourier transform infrared spectroscopy was used to determine the chemical nature of binding interactions. Apo stretching and bending frequencies are at 1645 and 1539 wave numbers. The copper-2 binding will change the frequencies and will provide insight into the coordination of copper-2. The symmetric and asymmetric frequencies for carboxylate residues indicate a unidentate and bidentate coordination. Stretching frequencies below 1300 wave numbers indicate hydrocarbon and serine stretching are not affected by copper. The second derivatives are nearly identical, supporting the notion that copper-2 is not influencing the stretching and bending of hydrocarbon and serine. Confirming the binding of terminal amine proves difficult due to the bending and stretching frequencies of the solvent and amide bands covering up those of the terminal amine. UV-Vis data indicates that there is 1 nitrogen binding to copper, suggesting a 1 nitrogen and 3 oxygen coordination complex.
In order to evaluate the binding thermodynamics of copper to C-peptide, we ran a thermogram of titrating copper-2 into C-peptide in both MOPS and MOPSO buffers. A near zero number of protons dissociate from C-peptide upon binding. From these titrations, we can conclude that copper-2 is binding at a 10 nanomolar affinity, which is entropically driven. This change in entropy may be caused by the desolvation of C-peptide and copper-2. It is not caused by structural rearrangement because there is no change in structure when copper-2 binds to C-peptide.
These past few months of research have led us to the conclusion that copper-2 binds to wild-type C-peptide entropically at the glutamic acid 3 and aspartic acid 4 residues as well as the N-terminus. The presence of copper-2 may be an important element involved in regulating C-peptide. However, the exact function and mechanism of C-peptide still remains a mystery. There may be other bioactive peptides that require metal cofactors to function. Future work would entail further investigation into how metals interact with new and established frameworks of peptides.
We would like to thank these parties for aiding us in our research. Thanks for
Thanks for
watching.
watching.